Welcome back, my dear students. So, do you remember what we have done in the last class? We just started with complex analysis, understood what a complex function of a complex variable is, how do we represent it graphically. So, I have told you, you have to have two planes parallelly to represent a function. Then we have seen what a sequence is, what limits of a sequence is, then continuity, and we have started with differentiation also. And you would have seen that the definitions are quite similar to your real analysis definitions. So, as I have told you in the last concluding session, we will start with what? Analytic or holomorphic functions. So, both are representing the same class of functions. You either call it analytic or else holomorphic. So, what is it? A complex valued function f of z is said to be analytic or holomorphic on an open set omega if it has a derivative at every point of omega. So, you can also use the term regular, okay, instead of analytic or holomorphic. So, all analytic functions you either say it is holomorphic functions, analytic functions or regular functions. It is important that a function may be differentiable at a single point only. Analyticity implies differentiability within a neighborhood of the point. This permits expansion of the function by a Taylor series about the point. If f of z is analytic on the whole complex plane, then it is said to be an entire function. So, as I have told you, the continuity of a function, the differentiability of a function, all these are properties of a point. You define it with respect to a point. So, you say a function is analytic if it is differentiable. So, is it only differentiability? No. What is it? It is differentiability within a neighborhood of a point. So, if I have to say that a function is analytic at a point z equal to z, now what it exactly means? It is differentiable within a neighborhood of the point. The differentiability at a single point is not enough here. And what will you call a function if it is analytic in the whole complex plane? You call it an entire function. Suppose f and g are polynomials in z, then h of z is equal to f of z by g of z, where g of z of course should not be 0. This is a rational function, okay. So, all polynomial functions of z, you know, it is entire, that means it is differentiable. A rational function of z is analytic at every point for which its denominator is non-zero. So, you do not have problem here also, same as in the real case. If a function can be reduced to a polynomial function which does not involve z bar. So, what is z bar? When you have learned complex numbers, you know that if z is x plus iy, z bar is the conjugate of that complex number. So, now we are dealing with functions of complex variables. So, if z equal to x plus iy is a complex function where x and y are real variables, so what will be your z bar? Z bar will be nothing but x minus iy. So, if you can express a function to a polynomial function which does not involve a term z bar, then you can say that it is analytic. So, I think it is little bit vague definition, but we will see some examples so that you will come to know how it is. Suppose you have a function f of f1 of z, x minus 1 minus iy by x minus 1 the whole square plus y square. So, here what you have to do? You have to substitute x as z plus z bar by 2 and y is equal to z minus z bar by 2i. How did you get those 2 points? See, if x plus iy is z, what is your z bar? X minus iy. So, I add those two, what do you get? Z plus z bar is equal to 2x. So, what is your x? X is nothing but z plus z bar by 2. In the same way, if I subtract those two equations, what do I get? Z minus z bar is equal to 2iy. So, what is y? Y is nothing but z minus z bar by 2i. So, let me substitute these values. See, what am I trying to do? I am trying to express my function f1 z in terms of z and z bar. Okay? In the place of x and y, I will replace it with the variables z and z bar. So, z is your x plus iy and z bar is your x minus iy. So, your f1z becomes what? X plus z plus z bar by 2 minus 1 minus I times z minus z bar by 2i, and the denominator becomes z plus z bar by 2 minus 1 the whole square plus z minus z bar by 2i the whole square. So, if I simplify, what happens? You get the function 1 by z minus 1. So, now you have reduced your function f1z into a function which contains only z, there is no z bar present there. So, what can you say about the function as per the definition of analytic function? So, you can say this function is analytic at all points, but there is a problem with one point. Which is that point? Z is equal to 1. So, why is that problem point there? You know that it is a rational function and the denominator should never be equal to 0. So, this function f1z is analytic at all points except z equal to 1. Now, another example. Okay? f2z is equal to x square plus y square plus 3x plus 1 plus I 3y. Same way we proceed. You substitute x as z plus z bar by 2, y is z minus z bar by 2i. See, you are again trying to find out whether there will be a z bar term once you simplify it by substituting these x and y in terms of z and z bar. So, if you succeed in getting a function which contains only z, then you can say it is analytic, but if z bar remains, what happens? That becomes a function which is not analytic. Here what happens after substitution? You can see that your f2z becomes z z bar plus 3z plus 1. So, what can you conclude here? You can conclude that it is nowhere analytic. Why? Because you have a term z bar coming in f2z after simplification. So, this is how you do it. See, but in order to test an analyticity, every time substituting x and y in terms of z and z bar, it becomes very difficult and it looks awkward also, because it is difficult for you to simplify and finally get a function f of z either in z or z bar. And it is quite time consuming also to reduce this expression to a form in which you want it. So, this method cannot be used when anything but algebraic functions are used, because your simplification takes more and more time. So, what is an alternative? Yes, there is an alternative which is coming to help you, and we call it as Cauchy-Riemann equations. So, if the function f of z is equal to u x y plus I v x y is differentiable at z naught equal to x naught plus I y naught, then the limit f dash of z naught is equal to limit delta z tends to 0 f of z naught plus delta z minus f of z naught by delta z. It can be evaluated by allowing delta z to approach 0 from any direction in the complex plane. I have told you, when you are in the complex plane, you are free to move in any direction, you are lying in the two-dimensional plane. Okay? Suppose it approaches along the x axis, that is delta z is equal to delta x. And what happens to the limit in that case? Then your f dash z naught becomes limit delta x tends to 0 u x naught plus delta x y naught plus I times v x naught plus delta x y naught minus u x naught y naught plus I v x naught y naught, the whole divided by delta x. So, as you all know, you can take the limit separately to the real and imaginary part. I applied the limit delta x tends to 0 to the real part and to the imaginary part. So, the limits of the bracketed expression are just the first partial derivatives of u and v with respect to x. So, how do your equation f dash z naught read now? It is nothing but dou u by dou x at x naught y naught plus I times dou v by dou x at x naught y naught. Now, suppose it approaches along y axis, that is your delta z tends to 0 along y axis. So, what happens to your delta z? It becomes delta y. So, your f dash z naught becomes limit delta y tends to 0 u x naught y naught plus delta y minus u x naught y naught divided by delta y plus I times limit delta y tends to 0 v x naught y naught plus delta y minus v x naught y naught by delta y. So, your f dash z naught becomes minus I times dou u by dou y at x naught y naught plus dou v by dou y at x naught y naught. So, by definition a limit exists only if it is unique. So, therefore, these two expressions must be equivalent. Equating the real and imaginary parts, what do you have? You have dou u by dou x is equal to dou v by dou y and dou u by dou y is equal to minus dou v by dou x. So, this must hold at z naught is equal to x naught plus I y naught. These equations are called the Cauchy-Riemann equations. Their importance is made clear in the following theorem. So, theorem is like this. Let f of z is equal to u of x y plus I v of x y be defined in some open set gamma containing the point z naught. If the first partial derivatives of u and v exist in gamma and are continuous at z naught, also it satisfies the Cauchy-Riemann equations at z naught, then f of z is differentiable at z naught. Consequently, if the first partial derivatives are continuous and satisfies the Cauchy-Riemann equations at all points of gamma, then you say the function f of z is analytic in the entire region gamma. So, let us quickly see an example. Suppose your f z is x square plus y plus I times y square minus x. So, what is your u and what is your v here? U is the real part of f z, v is the imaginary part of f z. So, u is x square plus y and v is y square minus x. So, differentiate it partially. You know that u is a function of x y, v is also a function of x y. So, how many partial derivatives do you get of first order? You get dou u by dou x, dou u by dou y, dou v by dou x and dou v by dou y. So, take the derivatives. You get dou u by dou x is equal to 2x, dou u by dou y is equal to 1, dou v by dou x is equal to minus 1 and dou v by dou y is equal to 2y. So, here the Cauchy-Riemann equations are satisfied only on the line x is equal to y, and therefore, there is no open disk here. So, by the theorem f z is nowhere analytic. So, it has to be equal in an open disk or in a neighborhood. So, here what happens, your function f z is not an analytic function because your CR equations is not satisfied in the neighborhood of any point. Now, let us see another example. So, here we have to prove that f of z is an entire function and you have to find its derivative. Okay? So, what is your function? You are taking your function f of z as e raised to z. So, e raised to z, how do I separate it into real and imaginary parts? That is e raised to x plus I y. So, it is e raised to x into e raised to I y, and what is e raised to I theta? It is cos theta plus I sin theta. So, I replace this as what? Cos y plus I sin y. So, now what is your u and what is your v? So, your u is e raised to x cos y and v of x y is equal to e raised to x sin y. Okay. Now, we proceed in the same way as the previous problem. You find its partial derivatives of first order. So, what is your dou u by dou x? Dou u by dou x is nothing but e raised to x cos y, you treat y as a constant. So, we have dou u by dou x as e raised to x cos y, dou u by dou y as minus e raised to x sin y, dou v by dou x as e raised to x sin y and dou v by dou y as e raised to x cos y. The first partials are continuous and it satisfies the Cauchy-Riemann equations. What were they? Dou u by dou x is equal to dou v by dou y and dou u by dou y is equal to minus dou v by dou x. You can see the CR equations are satisfied here. So, Cauchy-Riemann equations can also be called as CR equations. Okay. So, you can see that the equations are satisfied, also the first order partial derivatives are continuous here. Now, what is your f dash z? So, your f dash z is dou u by dou x plus I into dou v by dou x. So, what are you getting it as? You are getting it as e raised to x again cos y plus I sin y. So, you get e raised to x cos y plus I e raised to x sin y. This is nothing but your e raised to x. Go back in the way how we have separated it, you get it as e raised to x plus I y, and that is nothing but your e raised to z. And you know what? The derivative of e raised to z is e raised to z. See, now here we have seen an example in the case where your function, you have replaced it into the Cartesian form x and y, and there you have checked the CR equations. Now, suppose in order to separate it into real and imaginary parts, it is difficult for some functions if you do it in the Cartesian coordinate system. So, you may have to use the polar form of the function to proceed, and what happens or what is your corresponding CR equations in the polar form. So, what is the difference between x and y and the polar form r theta? You know the transformation from x y to r comma theta. So, how do you get it? So, you get it by substitution. X is equal to r cos theta and y equal to r sin theta. So, what is your r? R is nothing but square root of x square plus y square, and your theta is tan inverse of y by x. So, let us see what is the CR equations, the corresponding CR equations in the r theta form. So, your CR equations, so what is CR? CR stands for Cauchy-Riemann equations, and you know that in your Cartesian coordinate system it is nothing but dou u by dou x is equal to dou v by dou y, and dou u by dou y is equal to minus dou v by dou x. Okay? This is your Cartesian form equation. So, let us see what is the corresponding equations I will have to check when you are dealing with functions in r and theta. So, in that case your u and v will be functions of what? Your function f of z will be functions of r and theta. So, your partial derivatives will be with respect to r and theta here. Okay? So, here the corresponding equations are u r, or else I will write the similar notation, dou u by dou r is equal to 1 by r dou v by dou theta, and dou u by dou theta is equal to minus r dou v by dou r. So, in this case also what happens? You find the 4 partial derivatives dou u by dou r, dou u by dou theta, dou v by dou theta and dou v by dou r. All the 4 partial derivatives has to be found out, and you have to check whether all the partial derivatives are continuous, and also whether this equation, which is your Cauchy-Riemann equations in r and theta form, are satisfied. So, when do you have to deal with this kind of equation, or else some functions where it is difficult for you to evaluate it in x and y coordinate system? Let us see 1 or 2 examples in which you will have to use this formula for evaluating or finding out whether it is an analytic function. So, the first function, let us see f of z is equal to log z. So, how do I separate this into real and imaginary part? You cannot use z equal to x plus I y. So, instead what am I doing? You are substituting z equal to r e raised to I theta. So, now I get log of r e raised to I theta, which becomes log r plus log of e raised to I theta. It's a property of logs. So, log r plus it becomes I theta. So, now what is your u r theta here? U r theta is log r and v r theta is theta. Okay? So, again you will have to find the partial derivatives of first order with respect to r and theta. So, you have dou u by dou r, which is 1 by r, dou u by dou theta, which is 0, dou v by dou r, which is 0, and dou v by dou theta, which is 1. So, do you remember the CR equations which I have given you? What are the CR equations? UR is equal to 1 by r v theta and u theta is equal to minus r Vr. So, just check whether these equations are satisfied. Your partial derivatives are here. Yes, it is satisfied. You have dou u by dou r as 1 by r times dou v by dou theta, and since dou u by dou theta and dou v by dou r are 0, the second equation is also satisfied. But what can you say about the continuity here? See, you have dou u by dou r as 1 by r. So, the function dou u by dou r is continuous only at where r not equal to 0. So, when r equal to 0, what happens? So, when r equal to 0, your z also becomes 0. So, you can see that the function is analytic only at z not equal to 0, okay, because your partial derivatives are not continuous at z equal to 0. So, the conditions are similar, or the conditions which are similar, the similar CR equations has to be checked and the conditions continuity has to be verified. So, what can you say? Your f z is equal to log z is analytic at all points except z equal to 0. So, now once you have proved that the function is analytic, then you can find the derivative in the normal way actually. So, suppose I give you f x is equal to log x. What is its derivative? Its derivative is nothing but 1 by x, right? In the same way, what will be your f dash z? Your f dash z will be 1 by z, okay. So, you can keep in mind, once you have checked for analyticity for a function by taking the partial derivatives, all the 4 partial derivatives in this case, either in the r theta form or else in the xy form, check whether it is continuous and also the CR equations. So, here are the equations in r theta form and you have corresponding equations in xy. So, after verifying whether these equations are satisfied, and then if you have to find the derivative, you can directly differentiate here, okay. So, what is your f dash z here? It is nothing but 1 by z, and you can clearly see that it is not defined at z equal to 0. So, z equal to 0 has to be omitted here. So, another similar example where you will have to use the polar form is z raised to n. Say for example, so your example is f of z is equal to z raised to n. So, here also there is a problem if you go with x plus iy of z, because it will be difficult for you to separate it into real and imaginary parts, okay. So, what do? I put again z is equal to r e raised to I theta. You remember, you have learned whenever you have power of a complex number, you use r theta form or else the exponential form, okay, that becomes easier for you. So, r e raised to I theta the whole raised to n. So, what does it become? It becomes r raised to n e raised to I n theta, that is equal to r raised to n into, what is e raised to I n theta? It is cos n theta plus I sin n theta, okay. So, your u is u of r theta, right, because here your variables are not x and y, it is r and theta. So, r raised to n cos n theta, and your v of r theta is r raised to n sin n theta. So, in the same way you proceed, what is your u r, I write u suffix r. So, nothing but derivative of u with respect to r by treating theta as a constant. So, what do I get? N r raised to n minus 1 cos n theta, u theta will be, you are differentiating with respect to theta by keeping r as a constant. So, r raised to n remains. This becomes minus sin n theta into n. So, in the same way, dou v by dou r is n times r raised to n minus 1 sin n theta, and v theta is r raised to n cos n theta into n. So, again here you have to verify CR equations in r theta form. What was it? It was dou u by dou r is equal to 1 by r, dou v by dou theta, and dou u by dou theta is equal to minus r times dou v by dou r. So, you can easily verify that the CR equations are satisfied, and here there is no problem with continuity. See, all the functions here, it is not a rational function. So, you do not have to worry about the points where the denominator becomes 0 as in the case of log z. So, your CR equations are satisfied and all the partial derivatives are continuous. So, what can you conclude? You can conclude that your function f z is equal to z raised to n as per the definition or as per the theorem is analytic. Okay. So, now as I have told you, once you have proved that it is analytic, what can you do to find the derivative? You can simply differentiate it. So, what is it? N times z raised to n minus 1. Okay. So, what can you say about all these functions? Your function e raised to z, z raised to n, all those are entire functions. Okay. What is an entire function? It is a function which is analytic at all points in the z plane. So, an entire function is there is an exception of one point, even though it is analytic in the entire complex plane except a single point, still you call it an entire function. So, we have seen examples of functions which are entire. All your polynomial functions will be entire. Suppose it is a rational function, then what is the condition that you have to check? You have to check the denominator not equal to 0. So, now what all things have you learned in this class? We have started with analytic functions. We have seen how it is defined. So, when you go with the proper definitions and checking its analyticity, it becomes complicated. So, we have seen an alternative. What is it? The CR equations or the Cauchy-Riemann equations which will simplify your process of checking whether a given function is analytic. Okay. So, what are the things you have to check if I give you a function? The first thing is to separate it into real and imaginary part. Then you see what is your u, what is your v, that is your real and imaginary part. Find the partial derivatives of first order with respect to both the variables. Check the CR equations. We have done examples also. So, in the CR equations are not enough. Together with that, your partial derivatives, all the partial derivatives has to be continuous. And when we have seen some of the functions, you have seen some of them are very difficult to be separated into real and imaginary parts when you proceed with x and y. So, we have seen the corresponding equation in r and theta also. So, the CR equations, the corresponding equations in the r theta form has to be verified and the continuity has to be checked. So, if both are satisfied, you can say that the given function is analytic. And what do you call if a function is analytic in the entire plane? You call it an entire function. So, let us conclude here, because we have seen the analytic functions. Do some more examples on this and see what are the conditions which will make it not continuous, or else what happens if it is not defined at certain point. Okay, we will conclude this session now and we will start with a new topic which will be harmonic functions in the next class. Thank you for listening to me.